Hello. Hi guys, good morning. Welcome back to a new video. Ki hal chal? I hope you're doing good. In this, we're going to see construct the lexicographically largest valid sequence. Now, in this, we are saying that we are given an integer n. As you can see, you will be given some specific n. What do you do? You have to find a sequence which will satisfy this condition. That obviously, I will have an integer 1. It should occur only once in the sequence, and every other integer between 2 and n occur twice in the sequence. Now, every integer I between 2 to n, because 1 is already covered, so 2 to n are the remaining ones. The distance between the two occurrences of I is exactly I. So you will see that 3 and this 3 had distance of 1, 2, 3. 2 and this 2 have a distance of 1, 2. Same way 5 and 5 have a distance of 1, 2, 3, 4, 5. 3 and 3 have a distance of 1, 2, 3. 4 and 4 have a distance of 1, 2, 3, 4. 2 and 2 have a distance of 1, 2. Again, apart from 1, because 1 is separate. You have to build such a corresponding sequence. And again, they have written what a distance actually means. Now, you have to written a lexicographically larger sequence. And what thing will be lexicographically larger? Lexicographically larger is the thing which incorporates higher number first. Higher value first will lexicograph larger, which means if I ask you 71 or 29, you know that 7 occurs first and it is higher than 2. That is the reason it is lexicographically larger. Same way, I can simply compute what will be lexicographically larger. Obviously, I have to incorporate all of the n elements. Obviously, the 2 to n will occur twice and 1 will occur once. So in total, I will have 2 into n minus 1 elements. Why minus 1? Because 1 is occurring only one time. That is the reason I have these number of elements. So out of, let's imagine that you have some sequence. Again, let's imagine this number is 3, right? So if I have some 3 length sequence, obviously if I have a 3 length sequence, then I will always want that in the very beginning as higher number should come first for things to be lexicographically larger. And they have also explained it. Now, if we look at a very important thing, again, when I saw this one for the first time, I saw a pattern. The pattern was okay, 3 was here, and then 1 was here, then 5, 3, 1 was here. So when I saw the pattern for the first time, the problem for the first time, I was figuring out the pattern itself, but then I realized, oh, I looked at the constraints. The constraints were pretty low. They gave me a hint that I should not waste my time and I should try to find and go for all the possibilities, because this constraint says I can try brute force, which means this tells I can try for all the possibilities. But again, possibilities, they want me to try, but making sure that the possibilities are whatever is achievable and a form of answer. Achievable in terms of, obviously, let's say if I have a n is 5. If n is 5, the total numbers in the sequence which I will be making will be 2 into 5 minus 1, which are 9. As you can see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, for that, I know, okay, 9 is the location. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, I will always try to fill this position with the maximum value possible. I have numbers from 1, 2, 3, 4, and 5. I have numbers from 1 to 5. I will try to fill all these numbers, I will try to fill all these numbers, and I will always try to fill the largest possible available number first, which means that if this is empty, I will always try. Is it possible if I put a 5? Again, obviously, if I put a 5 here, I will also have to put it at the next location, wherever it is, at a distance of 5. But I'll always try putting up the highest possible value. Now, you will see it is simply based on recursion. But again, before we go on forward, the like target of this video is 100 likes. I love the love of yours in the last video, so please make sure that we complete the like target. Now, coming on back, we realize, okay, it's a simple recursion, but recursion says what? Recursion says that do as what is said. But here, do I have to do the same thing? No, I have to try for possibilities, which means I will start writing. Obviously, let's put up the indexes: 0, 1, 2, 3, 4, 5, 6, 7, and 8. So I will try putting up, let's say, 5. Whenever I will put up 5, this is, let's say, my current index, I will automatically have to find my next index 1, 2, 3, 4, 5. I'll find my next index and I'll also place my 5. Am I saying it is okay to place it? I'm not sure. Okay, then I will move on forward to my next location, which means I plus 1. I will see it is empty. How to figure out it is empty or not? By default, I can give the sequence values as 0. 0 indicates, okay, it is empty, nothing was placed, because I can only place values from 1 to 5, which means that anything apart from 1 to 5 is a default value which I can consider. Okay, now I will try placing 4. When I will place 4 here, I will say, okay, 4, which means that 1, 2, 3, 4. Can I place? Oh, obviously, I cannot even place a 4, because if I place a 4 here, the next index, obviously, for this current index, the next index will be I plus this value of nums of I, this value, which is 4, and it is already occupied, so I cannot place it. Okay, if not, then simply, try for a different value, or I should say a lesser value. Then I will try for a 3. If I try for a 3, I will simply place a 3 here and I will proceed forward. Okay, then here again I will try to place a 4, because obviously when I will move backward, I will try for 5, already visited. I will try for 4, not visited yet. So you see that I also need to maintain a used array that will say that, okay, what thing is visited. You can also name it as visited, what thing is visited and what not. And another thing which we realize is we will move back from largest to lowest number, largest to lowest, and try for the ones which are not yet used. That's another thing. Another thing we also realize that we will maintain a sequence. This is a sequence array which we are maintaining, which is of a size 2 into n minus 1, 2 into n minus 1. So 2 into n minus 1 is the size of this. So this is what we'll maintain. Obviously, we are going on to a specific index, so I'll always maintain the index as well. That, okay, at what index I am at. This is exactly of what we saw from the problem itself. Okay, let's try. As soon as I placed a 4, obviously I will try to place a 4 at 2 plus 4. 2 plus 4 is 6. I place a 4 here. Okay, that's okay. Then I will try placing a 2. Can I place a 2? Let's see. So the moment I placed a 2, which means, okay, I'll move on to the next index. Move on to the next index. Here, I'll place a 2. When I place a 2, 3 plus 2 is 5. Already occupied. Oh, in that case, I cannot place a 2 here. Okay, no worries. Try for the next value, which is 1. 1 is a special case. 1 can occur alone. Okay, in that case, great. I'll go on next index. Occupied, occupied, occupied. Okay, come here. When I come here, I realized, okay, I am at this current index and I will place a 2. If I place a 2 here, obviously, because everything else is visited, everything else is used, so it only 2 remains. If I place a 2, technically the next occurrence of 2 should come at 7 plus 2, which is 9, which is not even there, so I cannot place a 2. And also my array is finished. Oh, I cannot place a 2 at all, which means now I should go back. What I mean by go back, which means, oh, something went wrong. Obviously, I tried to place a 2 here as well. It didn't work out. I will go back. So you see, when we try to go back and try to correct things, we are saying we are trying for backtracking. Backtracking is, extended version of recursion. If you don't know what backtracking is, come on to backtracking crash course. Again, go to the Aryan, go to crash course section, come on to, backtracking, and just go and watch these videos. Again, this is a part of one video only, which is backtracking crash course. And again, this will be updated. This is also there already, so you can just watch backtracking and how it works. Again, it is just trying for all possible permutations, that's it. And again, if you want to practice more, you can come on to the practice problem DSA sheet. In that, come to backtracking course, and then you can practice the questions of backtracking as well. It is nothing but the extended portion of recursion. Again, I will not teach backtracking here. You can go and watch the backtracking crash course for that. But ultimately, it says that, okay, go back, reset things, and then come down again. What I mean by come down again? Come down says, okay, try for placing now. Although you tried 4 earlier, now you will try for value which is not used so far, which is next is 2. If I try 2, can I place a 2? Obviously not, because it will try to place it. I cannot place it. Okay, no worries. Go back. I can try a place 1. Yes, I can try place 1. Okay, in that case, move forward. Next index. In that, I will say, okay, try placing which is not yet used, which is higher value 4. Okay, I tried to place a 4. Can I place 4? 3 plus 4 is 7. So 3 plus 4 is 7. Yes, I can place a 4. Okay, now let's move on forward. Next location, next available element. Okay, 2. Can I place a 2? Yes. If I place a 2 here, next will be 2 here. Oh, now I have found a perfect candidate, and that's also my answer. You will see 5 3 1 4 3 5 2. Again, I want any of the first sequence which can give me the result. So you see what we did? We simply maintained a corresponding recursion. Now let's see how we will write the code. Again, the code will be pretty straightforward. It will say generate a subsequence. Obviously, I told that I need to get the sequence, which is a vector which I will be passing by address, and I will be updating this sequence. Again, everything will come up from the backtracking concept. Now, I also need to have a used array, right? I also need to have the current index, which I wanted. Now, I will have a quick check. What will check? Okay, if I have reached the end, which means my index has reached my sequence size, right? Sequence size, which means I have iterated through all the I have reached my final end, which means I was able to reach here. As you can see in this example, obviously this is a happy case. In the happy case, I can simply say that true. Again, I have always mentioned that you never know what to actually return unless you write your main recursive condition. So let's go on to the recursive condition. Then we come on that what we should write here and what we should return. Okay, let's proceed. Then I told that I will have to try for all the possibilities, which means that I will simply mention that start off from the highest value. So my number will start from the highest value. What is highest value? Highest value is n, which I can try. So I also should pass in n here. Then I will say that my num is more than equal to 1, and then num minus minus. In that case, you will try to find your, okay, obviously for a num, you will try to find your next index as well. So current index is I, which is this index. You have to find the next index as well. So you will find simply next index. What is the next index? Next index will be, again, technically it should be num plus your index, but if the num is 1, then your next index will be the current index only, because obviously if the num is 1, you only can place it one location, so it will be current index only. But if it is not, if num is not 1, then obviously your next index will be index plus num. This is your next index. Now I will have a simple check in which I will make sure that this current num is not yet used in this sequence which I am making. So I will have a quick check that if my this current num is used, then obviously there is not a possibility of even trying anything. I should continue. Or, but again, there are multiple other things. What if my num is used? Okay, that's good thing. But if my num is 1 and also my next index, maybe that is used or that is not available, or the location, the sequence is not available, then also I cannot do anything. This is exact same thing which we saw, that if I am placing a character and if the next location for it is actually busy or occupied in the sequence, I'm screwed up. So in that case, make sure that if the num is more than 1 and also your next index, right, the next index, it is out of the bound of sequence, which we saw in the case of 2. If it is out of bound of the sequence next index, right, in that case, sorry, sequence.size. In that case, I can simply say, bro, I'm screwed up. Bro, I'm screwed up. This is kind of screwed up scenario. Or I can also say that not only this, but also if that is a occupied location, which means that next index is occupied, which means it is not equals to 0. In that case as well, I am screwed up. I am screwed up. Now, okay, let's complete the brackets. Yes, in that case also I'm screwed up. So you see that this is how I can tell, okay, when I'm screwed up and when I'm not. If it is I'm screwed up, I should continue. When I say continue, I mean try for the next number, which can be a good candidate for you. If not, then I'm good to go, and I will simply say that sequence of the current index and also the next index should both become your current number. This means I am placing at index and next index this number itself. Then I will also make sure, okay, this is now used. So this is now used. So used of this number is true. Whenever I do that, I should make sure that I continue my recursion. Recursion is generate subsequence, sorry, generate sequence. Generate sequence with this sequence array or vector, I should say, and then my used, and then next index, right? And then n goes as is, because n is my candidate, which I can, again, I can declare it globally also, but yeah, this is how I can go about it. Now comes the backtracking part. Backtracking part says, because you are trying for all the possibilities, make sure that what thing you updated, if you did not encounter good things in your life, then go back and try to correct it. So again, anything while you do for going back, while you do as you go back, you do it after recursive step. So I will say that sequence of index and my sequence of next index should become to default value, which is 0, and also my used of my num should also become a false. And this is how I can try it. Now comes the fun part. Fun part is actually what I'm returning. I want to kind of stop my problem as soon as I get a specific sequence. So as soon as I get a sequence, I should stop it. So I can return a true or a false. Okay, return true, which means you stopped it. Which means that if I'm able to generate any specific subsequence, I should return a true. If I try for all the possibilities, but even if I'm not able to do it, I can simply return a false. And that's how I can write my entire problem. I can write my entire problem. Cool. Now, there's one small catch which I'm not sure if you guys missed or not, is that how or where are we checking that this index for this sequence is it even available or not? Because I'm only checking for next index. Where did I even check that the current index is even occupied or free? In that case, please make sure that have a condition that if your sequence of current index is not itself a 0, then bro, go and try for a next index, which means go and try generate the sequence, sequence for, again, there should be sequence for your next index, which means based in the same sequence, based in the same used, but it should be the next index, which is index plus 1. And that's how you are covering all the cases as what we discussed in the dry run as well. Now the complexity part, I will come on to it later on, but this is the code. Let's see the code quickly. Again, exactly same code. You see, exactly same code we have written along with just initialization of sequence of size 2n minus 1, used of size, covering all elements from 1 to n, and then calling my recursive function, and then ultimately generating the sequence. Now, if I ask about the time complexity for this, it is a simple permutation, which means if I come back to this specific array, you realize that you have 9 locations, 1 2 3 4 5 6 7 8 9. Now for that specific time complexity for first locations, how many options you have? You have 5 options from maximum to minimum. Obviously you will try placing it. Now this location has 5 options. Again, these are options, right? These are not the actual values, these are options. You have 5 options to place here. Now the moment you place a value here, whatever value is, any other value, again based on the index of the current, based on the value of the current value, the next index will also be occupied. So it ultimately means the next index is already occupied. Again, it can be anything. If I'm placing a 4 here, then it can be any other index, but yeah, one more index is occupied. So if I have 5 options to place here, ultimately one more index will be occupied. Okay, for the next location I have, again, how many options? One is already placed. One element is already placed. I only have 4 options remaining. Okay. As soon as I place another element here, one more index is also occupied. Again, why I am taking random indexes? Because just to give an inference that one more index is occupied. Now I will go on next. Okay, for now I have 3 options. Then again, one more index also occupied. Then I have 2 options. One more is also occupied. Then I have just one option. So you see that I have 5 into 4 into 3 into 2 into 1. These many number of options in the worst case, which I will have. But again, you will see that this is very worst, which ultimately also brings us to a fact that the answer for this will be 20 factorial. Technically, it might seem like 20 factorial is pretty large, which is actually large. So it might give you TLE, but not, because you see that we are doing pruning in this case. We are trying, as soon as we achieve any set of result, we are returning it back and not trying for unnecessary all the possibilities. Thus, because of pruning, we are able to achieve lesser complexity, and you will also see that at many times, again, there is no guarantee as such that you will always be able to place the highest value here, but there will be scenarios where the actual maximum value will be the best candidate. Again, I could have easily mentioned that, okay, I can always place the highest value here, so okay, 1 comes from there itself, and then 4 into 3 into 2. But again, still, just to prove that part, it's a bit tricky. You have to generate all the possibilities. Thus, we can easily say that because of pruning, because you are returning at the correct point in time, you are not trying for unnecessary possibilities, you will be able to achieve a lesser than n factorial time complexity, but still this time complexity will be there. So I can simply mention that my time will be O of n factorial. Now, the space for it, because obviously you are trying for recursion. In recursion, you are trying just to go on to all the possible indexes one by one, one by one, one by one. So in worst case, your recursive tree can go up to a depth of n. That is the reason the space will be O of n in this case. Cool. I hope you guys got it. If you have any doubts in backtracking, make sure to check out the backtracking crash course first. And if you want to practice the problems, go and check the practice problems for it. Bye bye. Take care. Please make sure that we complete the light target of the video, and that will be lovely. Bye bye.